Hello everyone, welcome to my talk. My name is Marcel, I am the lead engineer at Pendulum, and today I want to talk about smart contracts on Pendulum, and as an example project I will talk about OX Ember, and the whole spirit of this talk is bringing decentralized applications to life. So first of all I will talk about EVM versus WebAssembly smart contracts on Polkadot, then I will briefly introduce what cross-contract calling is, what chain extensions are and how they work. And then I will show you how you can deploy smart contracts and make them interact with each other. And last but not least, I will talk about the Ember project and why we need a tool like Wasm deploy. But before I start, I briefly want to introduce us, Pendulum. So our Polkadot chain is called Pendulum, our Kusama chain is Amplitude. And our vision is to connect fiat networks with the DeFi ecosystem. And so we do this by bridging stablecoins from the Stellar network to Polkadot. And it's not just limited to that, so it's not limited to our spacewalk bridge that is capable of bridging these stablecoins, but we of course also want to foster the DeFi ecosystem on Polkadot. And that's kind of the topic of this talk. So I will tell you how we do this, how we approach this topic. So first of all, let's talk about EVM versus WebAssembly smart contracts on Polkadot. First of all, the relay chain does not natively support smart contracts, but that's not a problem because that's not what it was meant to do. But of course, parachains can support smart contracts by adding pallets to the runtime, for example. Now let's first look at EVM smart contracts. So EVM is an acronym. It means Ethereum Virtual Machine. And this is basically a state machine or an implementation of a state machine that can run your smart contracts on Ethereum. And if you want to do this on Polkadot, then there are several implementations. There's, for example, the EVM palette that you can add to your parachain, and then you can actually support EVM smart contracts, or some parachains did some custom implementations with several improvements over the basic EVM palette. So yeah, the good thing about EVM is that, as you might know, the Ethereum ecosystem is quite big and DeFi is quite big on Ethereum. So there's lots of existing tooling for smart contract development with EVM, right? This is a huge advantage. And if we now compare it to WebAssembly, so you can actually deploy and execute WebAssembly smart contracts with the contracts palette. So any parachain can add this palette, and then you support them. And the main tool you would use to develop these WebAssembly smart contracts on Substrate is Ink. So Ink is the framework developed by Parity Technologies, and this really helps you out to leverage what Rust as the programming language gives you. And yeah, it's like the go-to framework if you want to do WebAssembly development on Substrate. Now, in this graphic, we can see at the top, we see a selection of programming languages or frameworks. So we have Solidity as like the most widely adopted programming languages for EVM smart contracts. Then we have Ink, the framework that I just introduced, that you can use for writing WebAssembly smart contracts for Substrate. And then we also have another format which is called WAT. This is WebAssembly text. And you can think of it as a very assembly-like language that you can use to like really do the most of your performance. So it's really low level, so it has the highest performance, but of course it's not very convenient to develop smart contracts with this language. Yeah, so you would then, what you implement in these languages or frameworks, you would compile it to either EVM bytecode or WebAssembly code. And then on the bottom, we see some executors. So for executing EVM bytecode, we have, for example, the Go Ethereum implementation, or we have on Substrate the EVM palette that I introduced. So both of these executors can execute the smart contracts either on Ethereum or on Substrate. And for executing WebAssembly code on Substrate, we have the contracts palette. And something worth noting is that you can see that actually Solidity can be compiled to EVM bytecode or to WASM code, because there's a tool called Solang, and this is a Solidity compiler that supports like WebAssembly on Solana and WebAssembly on Substrate. And this is super cool and super important because we use this to our advantage. But I will first show you how all of these things compare performance-wise. So we did some research on this, what I showed you on the previous slide. If you go down these paths, the different ways, then you can actually compare the performance of all these approaches. We did this last year. We did some research and experiments. And we have two different benchmark projects. As you can see, one is SHA-512, and the other one is odd numbers. So the one is just about hashing all over again, and the other one is about computing a certain number of odd numbers, multiplying them. And as we can see in this graphic, actually, if you go down the route of having a Solidity contract, then compiling it to EVM bytecode, and then deploying it on the EVM palette on Substrate, we can see that actually the execution time is highest, so it's worst. And if we then look at if we compile Solidity to the EVM bytecode and deploy it on the Go Ethereum executor, then it's better, but it's still not great. And something very interesting is that actually, if we don't compile this Solidity smart contract to EVM bytecode, but to WebAssembly and then deploy it on the contracts palette, you actually gain performance, so the execution time is less. And then also, if you implement the same benchmark in Ink, then you get even better performance. If you use the WebAssembly text format, because it's assembly-like and low-level, you get even higher performance. And last but not least, we have the palette. And you might wonder, okay, where is it? Is it missing? No, it's not actually. It's just so fast that it's not showing here. Okay, so the number is so little that you cannot see it in this graph. If you want to learn more about this, I recommend reading the Medium blog post, The Bright Future of WebAssembly Smart Contracts. But so the key takeaway here is that we decided that for our chains, we actually do not want to support an EVM executor. Okay, so we say WebAssembly is so great and it's so performant that we think WebAssembly is the future, and we don't want to have an EVM executor. Now, the problem obviously is that DeFi on Ethereum is so big, and there are so many great projects which have their contracts written in Solidity, for example, and on EVM, that we also want to attract these builders, right? And how do we attract them? We need to make it easy to build on Polkadot and on our chains. So next, I want to actually talk about how we solve this problem, how we can still make it easy for these builders to build on our chains. And this is not limited to our chains, it's just an example. So I just want to inspire you how you can also approach this topic without having an EVM executor. Now, this is basically everything we need, but let's break it down step by step. So let's say I'm a DeFi project on Ethereum, okay? And I have my smart contracts written in Solidity. And one of these contracts, let's call it mycontract.sol for a Solidity contract. Then using the Solang compiler, I compile it to an artifact, which has the extension .contract, doesn't really matter. But we compile it, and then we deploy it on our chain to the contracts palette, okay? So we have an instance of that. Now, since DeFi projects probably need to have access to some tokens, we need to actually provide this logic to this contract, right? So on Ethereum, you would usually have ERC20, and your contract would expect to have something ERC20-like that it can interact with. So some contract that has a name, a symbol, decimals, you can get the balance from that. You can use it to transfer tokens. And we need to provide that to this Solidity contract somehow. Now, what we did is we implemented the PSP22 standard. PSP means Polkadot Standards Proposal, and you can think of it as very, very similar to ERC20, but on Polkadot. So it has like most of the same interface. The functions are like they have the same name and everything. It's just basically the Polkadot version of ERC20. We implemented that. Then we deploy an instance of that. For the sake of the argument, I just call it USDC. And the next problem that we need to solve is we need to make them able to communicate with each other, right? So this might not work because we have a Solidity contract first and we have an Inc contract first. Maybe they are not able to communicate, but this is what I'm going to talk about next. So I will show you that this actually works. And you can also ignore the chain extension thing for now. I will also explain that later. So let's first talk about cross-contract calling. What is it? It's very simple. It's just the interaction between smart contracts, either on the same or a different blockchain. And basically, you have a call function, and then you provide that with the address of the contract that you want to call, and then you can also pass an amount. And basically, then the contract that you call executes the code of the function that you call and returns the data it generates. Now, I put some code, but please don't be scared of that. I'm just using it to make the point that it's so easy to actually do this cross-contract communication. So on the left-hand side, we have a little snippet of the name function. So this is part of the ERC20 standard. You have a name function. And what's printed in bold, this selector, is very, very important for this cross-contract communication. So you can basically think of it as we set an ID for this function, okay? This is not arbitrarily chosen. It has to be a specific ID. I will show you on the next slide how we actually derive this ID. But you can think of it as this is the identifier that I can use to call this exact function. And on the right-hand side, you can see a screenshot. So it's from Contracts UI, where I deployed an instance of this contract to our Rococo chain. And I deployed it not for USDC, but for the native token. Doesn't matter too much. But you can see here that the name function is called and the return value is native. Now, we deployed our Inc contract, our PSP22 instance. Next step would be to have a look at our Solidity contract. So here's a snippet of my contract.sol. And again, don't be too scared of all the code. We just focus on what's printed in bold letters again. Here we see the call function that I introduced on the previous slides. And token is the address of the contract that I deployed beforehand. And we can then call this address with using a selector. So basically, in this call function, we have to set the identifier that I set on the previous slide, right? Now you see here, okay, it says ABI.encode with signature and name. And the trick here is that what actually happens under the hood is, I'm not sure if you can see this too well, but so the signature of the function, we know what we expect from the other smart contract, right? We know, okay, I expect my ERC20 to have a name function, a decimal function, a symbol function. And to derive the selector, you basically just hash this signature using the Ketchak256 hash function. And then you get the identifier, right? And if you actually check, we have OX06FD. And this is exactly what I put as the selector, right? So as I said, it's not random. It has to be a certain one, a specific one. And then what we see here on the right-hand side, okay, I also deployed this contract. I compiled it using Solang. I deployed to the chain. And if we now call the name function, we get this OX2000 and whatnot hex value. And if you would put that into a hex decoder, then you would actually see that it says native. And this is so cool because that's all there's to it, basically. We showed that cross-contract communication works between our Solidity contract and our Ink contract. Now, this is not enough yet. This is great, but the next problem that we need to solve is we don't want to have isolated worlds, right? So probably most chains or many chains have their balances, their assets, their tokens living in their runtime, right? In some palettes. So we have the OML tokens palette, we have the palette assets and whatnot, and we somehow have to make this available to our smart contract space. And we can do this with so-called chain extensions. So chain extensions are also a feature of the Ink framework, and these allow you to configure your runtime and expose things to your smart contracts. By default, the runtime is limited, like in a way that not everything of the runtime logic is exposed, because that would be a super bad idea. We don't want to expose everything from our runtime to our smart contracts, because we cannot trust every smart contract to not do malicious things, right? So it actually makes lots of sense to limit this by default, and then it's up to the runtime developers to actually extend this functionality and expose logic like balances, where you can query balances, you can do transfers and whatnot, or for example, also price information, right? And so basically, our PSP22 smart contract, this implementation, it implements the ERC20 interface, but uses chain extensions to actually get the on-chain data. And that's all we need. Now, my contract can interact with something that is ERC20-like without actually knowing how it's implemented. That doesn't matter. And our PSP22 contract is able to interact with our runtime, and we don't have this isolation. We don't have to have USD tokens in our contract world that are unrelated to our on-chain world. This wouldn't make sense, really, right? And with this setup, we basically showed that you don't need to have an EVM executor if you follow this approach, right? You can actually make everything work in WebAssembly, and you can even profit from the performance benefits. Now, on to the next problem. I want to explain this problem with an example, and as an example, I will use OX Amber, and I will briefly introduce the project. So, OX Amber is a proactive market maker. Proactive means that it's using an external price oracle instead of relying on arbitrage, and it uses single-sided liquidity provision to reduce impermanent loss and fees and slippage. And basically, you have many single-sided swap pools and one backstop pool. It doesn't matter too much. The details don't matter too much. I'm just giving it as an example for making my next point. But if you want to learn more, they are launching on Pendulum in a few months, and they also have a white paper. So if you're interested in how they actually do it, then I can only recommend reading that. But on to the next problem. So in this graphic, I basically show some instances of smart contracts, right? So if we have a DeFi project, then it's very likely that this actually consists of multiple smart contracts and also of multiple instances of these smart contracts. So you don't just have one, but you have plenty of them. And here you can see some arrows, and these basically indicate some references between them. So we have, for example, the ERC20 instances of Euro and USD, and then we have some Oracle contracts that are referencing them. So you first have to deploy the ERC20 one before you can deploy the Oracle one, because one relies on the other, right? Not too hard to understand, but now let's go through this order. So if we look at all of them, then we first deploy the ones that don't have any outgoing arrows, because then they don't rely on something else, right? So first round, you could deploy these. Then second round, you could deploy the Oracle and backstop pool, because all of the dependencies are resolved, so to say, everything is deployed. And last but not least, you would deploy the swap pool. Boom. So you have to do 3 rounds, basically, and you can deploy all of this manually in Contracts UI. It's not difficult to understand what the order is, right? That's not the point I'm trying to make. It's just that it's so much work if you want to manually do this, because, okay, you deploy one smart contract, then you deploy the Oracle, but you have to provide the address of the contract that you deployed previously. And it might actually depend on multiple ones, so you have to pick all the right addresses and then copy paste, and then it's just so much work that we need to fix this problem. And we realized that this does not exist yet in the WebAssembly world. So we don't have a tool yet provided by Inc, for example, that you can use to deploy an ensemble of WebAssembly smart contracts. This tooling already exists in the Ethereum world. So for example, there's a tool called Hardhat that you can actually use to automate this deployment, and you can also use that for spinning up a testnet and testing, debugging, whatnot. But as I said, tooling for EVM smart contracts is way better already than for WebAssembly smart contracts. Now, this wasn't deploy tool. You can use that to automate this deployment flow. You can do that programmatically. Probably you would then eventually use a config file where you specify everything, but this is still in very early stages of development, so we are actually still building our prototype. I just want to bring this out to the world so that if you face a similar problem, that you know, okay, we identified this problem and we are working on fixing it. So if you are also interested in WebAssembly smart contracts and have a multitude of contracts that have some dependencies, then in a few weeks, you might also want to use or check out this tool. You can scan the QR code to get to the GitHub page. And yeah, that's all I wanted to say. I hope it was inspiring for some of you and you learned something. But if you have any questions, then feel free to connect with me on Telegram or Twitter, or you can ask them now or later at the venue, however you like. But that's it from my side. So any questions? No questions? That's a good sign probably, because it was so nice to understand, right? So, all right, then thank you for your attention.